we're going through 1.7 single replacement reactions from the unit Foundations in Chemistry Part 1. We will be predicting products of the 5 basic types of reactions and evaluating the impact these reactions have on society and the environment. And by the end of this lesson, you will be able to understand what a single replacement reaction is, know how to use the activity series chart to determine if a reaction will proceed, and use the solubility rules to determine the states of matter of each reactant and product. Single replacement reactions, their characteristics is that an atom of a lone element replaces the atom or atoms of an element in a compound. Metals replace metals, or cations replace cations, and nonmetals replace nonmetals, or anions replace anions. Metal-cation replacement for this reaction, A plus BC yields B plus AC. If A and B are cations, A replaces B in the compound. So say A is sodium, that's a cation. We know it would have to replace B, which maybe is potassium chloride. A would have to replace B. Now, if D, or our lone element out front, is an anion, we have non-metal anion replacement. So really it's the exact same formula. It just depends on what that lone element is. So if D is Cl2, that's an anion, D and F would have to replace each other. So if we had K Br, our negative ion, remember Cl is our anion, it's the negative one, has to replace our negative ion. Those two would have to swap. And this nonmetal replacement usually involves halogens. There are some restrictions on the replacements of reactions. We need to look at our activity series, which is a chart that tells us how reactive our metals are. And it determines whether or not a single replacement reaction will occur or not. For our metals, we need to look at the activity series chart of metals arranged in order of decreasing activity. And for nonmetals or halogens, as you move down the group on the periodic table, the activity decreases. So fluorine would be the most reactive at the bottom, and then as you go upwards, fluorine would be the most reactive at the top, and as you go down, the activity decreases. So a single replacement reaction will not occur if the reactivity of the pure element reactant is less than that of the compound reactant. So I like to think about this as, if we just we're going to think about a relationship with a man and woman in this case. I do recognize there are several types of relationships, but this is just a good visualization. So if we have a dude right here and a girl, we'll put her in a dress, and a guy, and they're in a compound together, right? If the guy, these are his muscles. If the guy that is by himself, or the element that's by himself, is stronger than the guy in a pair, then the stronger guy will be able to kick out the guy in the couple. If that's not the case, say, we'll erase this, and say we are guy that is in the couple is stronger he would be able to hold on to his woman, and the guy that's single wouldn't be able to get him. So in this case, there'd be no reaction. There'd be no change of place or no reaction. If the lone guy was stronger than the guy in the couple, there would be a reaction. And we need to look that up on our activities series chart. So we look up tin and we look up sodium on our activities series chart. And depending on your chart, for ours, the farther down the element is, the more reactive it is on the chart. So we find that sodium is much stronger than tin, so there would be no reaction. It will occur if the reactivity of the pure element is greater than that of the compound reactant. So in this case, zinc is stronger. If we look then hydrogen. If we look on our activity series chart, zinc is farther down the chart, so we know it's stronger, which means a reaction will occur. And then we predict our products and swap our cations. In this case, zinc is a metal or a positive ion, so we would go A, B, C, and A would go with C, and B would be left out, and the reaction would proceed. Again, just like double replacement reactions, we could write this A plus BC yields B plus AC. These two are the exact same forms. Again, it's 4 plus 2 or 2 plus 4. That means the exact same thing. Identifying single replacement reactions. Single replacement reactions will always have one lone element and one compound on the reactant side and the product side. So our reactants will always be one lone element and one compound. Products will always be one lone element and one compound. Right? If we look back at this, we have one lone element, it's by itself, and then a compound. There's two things together on both our reactant and our product side. So steps for single replacement reactions. We need to use the activity series chart. So again, our steps for single replacement reactions: use the activity series chart to determine if the reaction will proceed. And if it doesn't proceed, write no reaction, and then you're done. If it does proceed, you need to predict the products, show the states of matter, and if you have diatomic elements, remember that it's a gas. If you have a lone element that's not diatomic, it's a solid, okay? And you look up the compound, the compound on the reactant side is always aqueous, just like double replacement reactions, the compounds on the reactant side are always aqueous, and you have to look up the solubility to find the state of matter on the product side, and then you go ahead and balance the chemical reaction. So an example here, so our first step, it says use the activity series chart to determine if the reaction will proceed. We look up aluminum and hydrogen, and in this case, aluminum is stronger than hydrogen, so the reaction will proceed. We are good to go. We need to predict the products is our next step. Aluminum is a positive element, it's in metal, so it's a cation, which means we go A plus BC yields B plus AC, and B comes out. Hydrogen is by itself, and we know we can't just write hydrogen by itself. It's a diatomic element. We need to write H2. And then A and C go together. Again, we look up the charges, Al3 plus and SO4 2 minus. We swap and drop those charges. We get Al2 and in brackets SO4 3. I'm going to rewrite our reaction and then we'll do states. So aluminum plus sulfuric acid yields H2 plus Al2SO4. We can do our states. So by itself, anything by itself is a solid. Any element by itself is a solid unless it's diatomic, then it's a gas. The compounds on our reactant side are always aqueous, and the compounds on our product side we need to look up. If we look that up on our solubility chart, we look up sulfate. Sulfate paired with aluminum is under all others, which is soluble, therefore it is aqueous. And then we have to balance our reaction. We take a look at, oh, I forgot a lovely 3, which is important. We look at our polyatomics first for balancing. We have sulfate with 3 on one side. We need to make sure we have 3 on the other side. We have 2 aluminums on one side. We need 2 aluminums on the other side. And if we look at how many hydrogens we have 6 on one side. We need 6. So we should be good to go. If we look at the next example, Cl2 plus Ki, we need to take a look at our periodic table. And like I said, fluorine is the most reactive, and as you work your way down, it becomes least reactive. So fluorine chlorine is next. It's more reactive than iodine, which means this reaction will go ahead. And if we take a look, chlorine is an anion. It's our negative ion. So in this case, we are going to be getting DEF, and F comes out, and E and D go together. So F comes out, that's iodine, and we know that iodine is a diatomic element, so it has to be I2. And then K and Cl go together. So it goes KCl when you write out their charges and swap and drop them. Again, it's good practice to write out your reaction one more time. I2 plus KC, oops, missed my K, Cl. And then we need to write out our states. So any element by itself that is diatomic has to be a gas. A compound on our reactant side is aqueous, and a compound on our product side we need to look up on our solubility table and see if it's aqueous or solid. And if we look up chlorine on our solubility table, it's paired with potassium, which falls under all others. Therefore, it's aqueous. And lastly, we balance. We have 2 chlorines, we need 2 chlorines. Now we have 2 potassiums, we need 2 potassiums. We have 2 iodines, we have 2 iodines. We're good to go. And 2 more examples here. Lithium and water, so HOH, remember that's water. Lithium is the most reactive element, so we know we are good to go. That's how I always remember which direction my table is going. If the most reactive element is lithium and it's on the bottom, it's lithium, then it goes from the weakest to the strongest on the bottom. Or if it's lithium's on the top of my table, because some charts are a little bit different, I know it goes from the strongest at the top to the weakest on the bottom. Lithium is the strongest. So, our reaction's going to go ahead. We've known this from our activity series. And lithium is our positive metal. So we are going to use A plus BC yields B plus AC. And hydrogen pops out. We know it's diatomic. We need to write H2. And leaves lithium with our hydroxide. And if we swap and drop those charges, we get LiOH. Again, good practice to write out I'm going to write it out as H2O. I find that a little bit easier than HOH. H2 plus lithium hydroxide. We do our states. An element by itself is solid. If it's a diatomic, it's a gas. We can't forget about water being a liquid, and we need to look up lithium hydroxide on our solubility chart. If we look that up, we find out lithium hydroxide is an aqueous. And then we balance our reaction, which it looks like there's one lithium on either side, there's one oxygen on either side. Oh, we got 2 hydrogens on one side and 3 on the other side. So we got a problem. We need to balance our hydrogens. So I might need to add a 2 in front of lithium hydroxide, which means I need to do a 2 in front of lithium. To get the correct amount of lithiums, I now have 4 hydrogens, so I'll need a 2 in front of hydrogen in front of our water, and then we should be balanced. Our next example is calcium and aluminum phosphate. We take a look at that on our activity series. Calcium is farther down than aluminum, so we're good to go in this case. And it is a cation, so we go A, B, C yields B plus A, C. And B is aluminum by itself, and calcium 2 plus pairs with phosphate PO4 3 minus. If we swap and drop those charges, we get calcium 3 and then in brackets PO4 2. And since I did such a terrible job of writing in the first place, like I said, rewrite it out again. Aluminum phosphate yields aluminum plus calcium phosphate. Better looking. Well, you can understand it. We write our states out. Calcium is a solid, it's by itself. Aluminum is a solid by itself. Again, this is the one always people forget. Compounds on our reactant side are aqueous, unless they're water, like in the previous example. And then we need to look up our compound on our product side, on our solubility chart, which, when we look at phosphate, it is attached to calcium. It falls under all others, which ends up being a solid. There we go. Well, we're good to go. Let's double check this one just to see if it is no reaction or not. We have iron, and now this one we need to be a little bit more careful with. Iron 3, right? This 3 belongs to the iron, so we need to look up iron 3 plus and and silver. And silver is the one by itself. So if we look up silver, silver is not very reactive. And iron, actually both irons are much more reactive. So iron is going to grab hold to its oxygen. It's not going to let go of the oxygen. Therefore, this will be no reaction. Just write no reaction and be done with that guy. There we go. That's single replacement reactions.